first topic I'm going to start with under bending moments and shearing forces is that of a cantilever with an end load. So I click on this. This is a cantilever with an end load. First thing to do here, you can see this cantilever has is fixed at B and free at A. So I can use this to apply the load. As I apply the load, you can see the shear force at any point here is dependent on the load and independent on the moment. So but the bending moment is a product of the force and the perpendicular distance. So if I apply the span length and then consider a section at any point, you see that the bending moment values have been generated as long as the shear force value remain unchanged, but whenever I increase the load, it changes. So here you can see that the shear force, the bending moment diagram is being drawn alongside with the shear force when the load is being increased or decreased. So it alters the bending moment and the shear force values. While that of the sectional distance alters the bending moment alone, because the shear force is independent of the cross section or the section or the span, while the bending moment is dependent on the length, the distance under consideration. So as you consider any distance, 3 meters, 2 meters, or whatever value, you can use this to make it exactly 3 meters. If you want to make 2 meters, you use this to perfect it to 2 meters. So you can see that as we increase the load or decrease the load, or increase and decrease, the bending moment changes and the shear force values also changes, because it depends, the bending moment depends on the load and the distance under consideration, while the shear force depends only on the load. So this is the simulation which can be carried out using this software Saapplet. You can use it to perform the simulation of a cantilever with an end load. So another case we will consider is that with a UDL, a cantilever with a uniformly distributed load. You can see a cantilever fixed at B, free at A. So we can use this to apply the load. We use this to apply the total length of the cantilever to whatever we want, and we use this to consider a section. So at any section, you can see that the shear force and the bending moment diagram are being drawn. So at any section, and you can see from here the section or the sectional distance is not supposed to exceed the total length of the cantilever. For total length, whatever length we're using here, you can see as you're decreasing the length, the sectional distance is also decreasing, because it is supposed to be less or equal to the distance. So you're considering a section from this point A to B, which the total length is 5.9, and the sectional distance can be anything less than 5.9. So we are considering at any section less than 5.9 or 6.8, as you can see. As you're trying to exceed the total span, the span continues to adjust. So use this to simulate that, and you can see the values are generated automatically. So this software helps you in simulating the shear force, or finding the shear force and bending moment values of a cantilever with a uniformly distributed load. So another case we will consider is a cantilever with a uniformly distributed load and a concentrated load at the free end. So you can see this is a cantilever that is fixed at B and free at A. So we use this to fix the point load or the concentrated load. Then this to apply the UDL. Then we use this to set the span to whatever value we want, and we use this to cut a section across it. So as we cut a section, we'll be able to find the shear force at X, this point XX, then the bending moment. We use this to find the bending moment, and the shear force at B, we can find the value. So you see that as you consider the section, you can see the diagram is being drawn, the shear force diagram as well as the bending moment diagram are affected whenever we vary these results. Look at cantilever carrying a UDL or uniformly distributed load for a part of its length. from the free end. So here we use this to apply the load. You can see this is the cantilever in question. It is fixed at B and free at A. So we use this to set the load, set the value of the load. We set the span length. We use this to consider this section at any section under consideration, the sectional distance. So we use this to set the sectional distance. So as you increase the load or decrease the load, you see that the value of the shear force changes alongside with the bending moment. So use this to simulate this. As you do that, you see that the shear force and the bending moment diagrams are drawn. You can see whenever we decrease the span, you see that it affects the shear force and the bending moment values. So with Saapplet version 1.5, you can analyze a cantilever carrying a UDL for a part of its length from the free end. So next, we look at a cantilever carrying a load whose intensity varies uniformly from 0 at the end to W per unit run at the fixed end. So this is the cantilever in question, fixed at B, free at A. So we are trying to use this to apply the UDL. You can see that the load varies, is maximum at B and minimum at the free end A. So we use this to set the span. So use this to set the load to whatever value we want, and then consider the sectional distance. So distance at any section from the free end. So as we do that, we see that the shear force and bending moment diagrams are drawn. So you can see what we have here. So it was the shear force as well as the bending moment diagram. So with Saapplet 1.5, you can be able to analyze a cantilever carrying a load whose intensity varies uniformly from 0 at the end to W per unit run at the fixed end. So let's look at another case of a cantilever carrying a load whose intensity varies uniformly from 0 at the fixed end here to W per unit run at the free end. So here we can apply a UDL. You can see the UDL is maximum at the free end, which is A, and you can see we can use this to set the span. So as we set the span, and then we can also consider at any distance. So if you're coming from B, from the fixed end, you're cutting a section from B, you can see that as you vary the sectional distance, it affects the value of the shear force as well as the bending moment. So can you see what we have here? So with this software Saapplet, you can simulate a cantilever carrying a load whose intensity varies uniformly from 0 at the fixed end. We see from 0 at the fixed end to a maximum value at the free end. So we'll consider another case, a simply supported beam carrying a point or concentrated load at any part of the span. So this is a simply supported beam. You can see it simply supported at A and B. We use this to apply the load. After applying the load, we set the span of the beam to whatever value we want and consider where do we want to keep the load. Where do we want to keep the concentrated load? Do we want to point it at the center or to anywhere? So as you point it, you see that the shear force values and the bending moment diagrams are drawn at the same time. So you see it instantly, they are computed. So the values are affected whenever we change the load or we alter the span. You can see. So with this, we can draw or simulate a simply supported beam carrying a concentrated load at any part of the span. So consider a simply supported beam carrying a UDL. So here we have a simply supported beam, simply supported at A and point B. So we use this to apply the UDL. Apply the UDL to whatever value we want in the span. We use this to set the span, and then consider any distance at any sectional distance from B to A. So at any distance, you can see that the values of the shear force and the bending moment are shown, and the diagrams are drawn. The software Saapplet version 1.5. So as we also increase the load, you can see that the shear force values and the bending moment values are being altered. So with this software, we can draw the shear force and bending moment value on diagrams of any given load and any sectional distance. So here we'll consider another case: simply supported beam carrying a load whose intensity varies uniformly from 0 at each end to W per unit run at a new span. So here we have a simply supported beam, simply supported at A and B. So we also increase the UDL. You can see the UDL is maximum at the center, minimum at the fixed at the simply supported end. So here we set the span to whatever value of our choice and consider the distance from B, sectional distance from B. So whatever value we want from B up to the center. So as we do that, you see that the shear force values and the bending moment values also changes, and the diagrams are drawn, as you can see here. You can see how the shear force and the bending moment diagram varies when the load is increased and when the span is also altered. The sectional distance are also altered. So with this software, Saapplet 1.5, you can be able to simulate a simply supported beam carrying a load whose intensity varies uniformly from 0 at the supported end to maximum at the middle. So here we'll consider another case: simply supported beam carrying a load whose intensity varies uniformly from 0 at each end to W per unit run at the other end. So let us see what we have here. A simply supported beam at point A and B. We apply the UDL. So apply the span, and then when we consider the section, you see that the load is drawn. It is maximum at A and minimum at point B. So as we alter the sectional distance, you see that the values of the shear force and bending moment, as well as the reaction at point A and B, are being shown. So you can see the diagrams are drawn. So as we alter this, you can see what we have here, how the shear force and the bending moment value changes. You can see what we have here. So as we increase the load or decrease the load, you can see what we have. Increase the span. So the bending moment diagrams are shown. So next we consider the last part of the example we have here for bending moment and shearing forces. This one is for simply supported beam with equal overhangs and carrying a uniformly distributed load of W per unit run over the whole length. So we'll apply the UDL for the whole length, pick whatever value we want, we'll set the span, and then we'll consider the distance. See that as we consider a distance from 0, you see what we have here, and see that the shear force and bending moment diagrams are drawn as we have here. You see what we have, which will increase. So we'll vary this.